Okay, so let's get started on online lecture number 1. So the topic of this lecture is going to be Taylor series. So in the first lecture, I spoke about and we solved the problem for a pendulum. And during that lecture, I used a so-called small angle approximation. And the reason we were able to do that was because of some reasoning that I'll talk about today using Taylor series. Okay, so by the end of this little online lecture about Taylor series, you should understand exactly how a small angle approximation works, as well as some more information about Taylor series. Okay, so I definitely recommend that you become very familiar with Taylor series. I would file it under the category of math topics you should know very well. So it's used all the time in physics. So you should take the time to learn it. Okay, so what is it good for? So as I mentioned already, it's often very useful when you're trying to find an approximation for a function under certain conditions or in certain parts of that function. So let's just write that down. So what a Taylor series is for us anyway, it's a way to approximate a function. And this is where it gets pretty cool and kind of interesting. We're approximating the function at and around a point using only the derivatives at a single point of the function. So using the function's derivatives at a single point. Okay, so that's what it is for. At least that's what we use it for. There's a lot of math having to do with Taylor series, which I won't go into in great detail, but for our purposes, this is what we use it for. Okay, so if you have some function, function f of x, and this could be any old function. In our case, we're often working with more well-behaved functions than the one I've drawn here, like sines and cosines and exponentials. But for the moment, let's just think of it in general terms. So if we have such a function and we want to know how to approximate it near a particular value of x. So let's just pick a particular value of x, say right here. Let's say that's when x equals a, right here at this point. So if you go up, so we're talking about approximating the function in this territory around where x equals a. So what does f of x equal at that point? It's f of a. And what we're going to do is use the Taylor series to approximate the shape of this function nearby the point where x equals a. So if you imagine zooming in here and looking at that, just that little bit of the function there nearby x equals a, let me see if I can redraw that in a zoomed in form. Something like that is what I drew. So if you zoom in there, here's our zoomed in view of f of x around the point x equals a. So again, we're just redrawing this around the point x equals a. Okay, so the goal for, and what we're trying to use this Taylor series for, is to get this shape right here. Okay, so the math and the way you write down a Taylor series is as follows. If we want to say what is the Taylor series expansion of f of x near x equals a, then it is the following. So it's f of a plus, now this is the first derivative of f, that the prime here, the way when I'm writing a prime, the prime indicates the first derivative of x, of f of x with respect to x, evaluated at the point A, and then we divide by 1 factorial, which is 1. I'm writing out all the details here because you'll see a pattern as we add more terms to this Taylor series. So that's the first term. The second term, the third term of the Taylor series is the second derivative of x evaluated at a divided by 2 factorial times x minus a squared. And then you can keep adding terms here. It's an infinite series, so it's plus the third derivative of f evaluated at the point a divided by 3 factorial times x minus a cubed, and so on. Okay, so now let's take a minute to see what does that look like. So I mean, first let me point out, so this set of terms that we're adding together is going to give us this shape, right? That's what we're trying to get from it. And all it really is, as a function of x here, it's just a polynomial, right? This is just a constant term, this is a linear term, this is a quadratic term, this is a cubic term. Everything else is just a bunch of constants. So this is a constant, this is a constant, well, that's a constant, and this is a constant. So these are just the coefficients of a polynomial. And so what we're doing is taking this function and representing it as a sum of simple polynomials as a constant value. So let me get my eraser here. Or okay, let's draw the approximated version of f over here. So the first part of this approximation is let's put an orange box around this guy. So the first part of the approximation is this term, f of a. So that's the first part of the approximation. So to add up these different pieces to get this thing, the first part you're adding up is just a flat line. That's f of a. The second part we're going to add up is this linear term. Right, so and it's a linear term with a slope that's exactly equal to the derivative of f at that point A. So in this case, I've actually picked a point which is at a minimum, so the derivative is close to 0 right there. So this term is small, doesn't contribute much. Maybe it's slightly non-zero. So you add on to this something like that. That's supposed to be a straight line. And then the next term is the quadratic term. And in this case, in this particular example that I've drawn, the quadratic term is going to contribute quite a bit. It has a large second derivative of a with, or second derivative of f with respect to x at that point A. So this coefficient is fairly large, and it's multiplying this quadratic term. So you add in a quadratic. That's what the purple curve is, the addition from this third piece here. And then maybe we'll also include this cubic term. So the cubic term is taking the third derivative of f and evaluating it at the point A and adding that in as well. So you get some addition of a cubic variable too. So that's this kind of picture. So you add up these three pieces with the correct coefficients, the correct coefficients being that, and that, depending on the derivatives, and you get something close to this black curve. Okay, so that's literally what this Taylor series is giving you. It's giving you a way to recast the shape of this curve in terms of a bunch of polynomials with coefficients that depend only on the derivatives of f at the point you're interested in, nearby the point you're interested in. Okay. Now, let's then go ahead and see how this might be useful for approximating, for example, the small angle approximation with trigonometric functions like sine and cosine. Okay, so for let's figure out. So an example. Let's consider the small angle approximation of sine. We'll say sine of x. Okay, so that's the example we will do now. And we use this to solve the pendulum equation of motion in our lecture earlier. Okay, so sine, as we know, sine as a function of x is just this wavy function. And nearby, so this is sine x, function of x, nearby x equals 0. That's what we're talking about when we're talking about the small angle approximation. That's saying x is small, x is much less than 1. So that's what we're saying with, so we're talking about x much less than 1. So we're just in this territory around the origin. What does sine look like? So let's go ahead and apply the Taylor series to the function sine around the point x equals 0. So that's what we're going to write down. Taylor series of sine near x equals 0. Okay, so again, we're just using our formula here, starting with, so this is, instead of a, we're talking about 0, right? Near x equals 0. So sine of 0 is 0. So the first term in the Taylor series is 0. What's the second term? The second term is the first derivative of sine, which is cosine. Cosine evaluated at 0 divided by 1, and then multiplied by x minus 0. Right? That's the second term here. Now we add the third term. We have the second derivative of sine, which is a cosine, and then take the derivative of that, you get a minus sine, again evaluated at 0, divided by 2 times x minus 0 squared. Some of these terms are going to disappear, of course, that's 0. Let's add the third term in there. We've got the third derivative of sine, so we take one more derivative and you have a minus cosine evaluated at 0 divided by 3 factorial. So we could go ahead and write the factorials down if you want. Times x minus 0 cubed. And let's go ahead and do one more term. Why not? So we'll have a positive sine of 0 over 4 factorial x minus 0 to the 4. So, and on we go. So let's get rid of the term. So this is cosine 0, that's 1. Let's use a different color here. So this guy is 1. This guy is 0. This guy is 1. That's 0. So we're not left with too much here. We just have, this is equal to x, that's this first term, 1 times x, 0 minus x cubed over 3 factorial plus 0. That next term would be x to the 5th over 5 factorial. Then the next term would be a minus. We could have went ahead and done all this, but I just want to keep writing out the terms so you'll see the pattern that is emerging here. So that is the Taylor series, and it continues, of course, so minus dot dot dot. That is the Taylor series expansion of sine. Nearby x equals 0. So then what is the small angle approximation? Let me just erase some of this over here. So the small angle approximation, when x is much less than 1, what we have then these terms are getting progressively smaller and smaller, right? If x is much less than 1, then x cubed is tiny. X to the 5th is even tinier. And not to mention they're being divided by larger and larger exponents. So these terms, as you go from this one to that one to that one, are getting smaller and smaller and smaller and smaller. So when we're in this regime of small x, sine x is pretty well approximated by x. And that is that's the first order small angle approximation of sine, first order in x. So if someone asked you to do it to the next order, the next highest order in sine, then you would also include the x cubed term. And let's see. Similarly, the expansion for cosine is as follows. So the cosine, let's go ahead and write it down here. Taylor series of cosine near x equals 0. So that thing is going to be equal to cosine of 0 plus, actually we're taking the derivatives. The first derivative is minus sine evaluated at 0 over 1 times x plus, minus cosine of 0 evaluated at 0 times x squared plus sine of 0 over 3 factorial x cubed plus dot dot dot. And so what this turns out to be, so cosine of x equals, this term is 1, cosine of 0 is 1, this term is dead, it's 0, this term is minus x squared over 2 factorial, the next term is dead, next term is going to be a positive x to the 4th over 4 factorial, and so on. So, if you were to compute the first order, the lowest order approximation of cosine for small angles, it's 1. So that's only for the case when x is very small. And if someone asked you to compute the next highest order approximation of cosine for small angles, then you would include this quadratic term as well, the x squared over 2. Okay. Maybe just one more note, which is that for certain special functions, including cosine and sine, this expansion, if you continue it out to all infinite number of terms, is exactly equal to the full function. It's not just an approximation. So there are certain functions called analytic functions. If the analytic function is analytic over the entire range of the function for all x, then that means the Taylor series is exactly equal to the function. It's not just an approximation. That's not the case for all functions. It's true for cosine, sine, and e to the x, It's not true for other functions like log x or e to the minus 1 over x squared, a couple other functions which don't in general exactly equal their Taylor series, but some of them do. Okay, so that's it for Taylor series. All right.